So we'll go ahead and get started here. Did you guys have a chance to watch the video last night? Okay, did it make sense? Okay, so hopefully it, for the most part, made sense. It will more once we do some of the practice problems in class, but we're just going to kind of build on what we talked about there. I mean, essentially, what you have to keep in mind here is the main thing we've been focused on at this point is how concentration changes the rate of a reaction. Okay, and so we talked about yesterday in class. We talked about all those different ways you could change the rate of a reaction. Okay, the big, I guess, three that we're really going to focus on are concentration, temperature, and catalysts. And so what we've been talking about so far is how does concentration affect the rate? Excuse me. I hope I don't have a coughing fit in the middle of this too, because that would be embarrassing. But we were talking about how concentration affected rate yesterday, and essentially there. Let's see, let me find my spot here. I mean, essentially the thing you have to understand about concentration and rate is that you cannot predict how a reactant is going to affect the rate of the reaction without doing an experiment. You can't know. Okay, so it's very tempting, to look at an equation like this and say, okay, the stoichiometry here tells me that this should, be a second order with respect to the N2O5. Okay, when you're trying to figure out the order of the reaction, you can't do it that way. You have to actually look at a set of data to figure that out. Okay, and so that's that. That's really the main thing that I wanted you guys to understand from concentration and rate stuff. And then just basically once you get that down, let me go ahead and go to the slides here. Then it's just kind of a matter of knowing how to write the rate law. The rate law is always going to look like rate equals K, which is your rate constant, times whatever affects the rate of the reaction. Okay, so and then your exponents in the rate law, that will tell you the order with respect to whichever reactant we're talking about. Okay, and so again, we'll get into that more in class today. We'll do a lot of practice on this stuff, and hopefully you'll feel really comfortable with it after you see what the AP exam expects you to be able to do with it. Okay, it's really not that difficult. So now we're going to talk about how concentration changes over time, because I sort of mentioned this yesterday, but if you think about it, a reaction is going to slow down over time as the concentration of the reactants goes down, right? Because as we run out of the reactants, now there's less of them to come into contact with one another, and they're actually that's going to slow down the reaction, okay? So this is the first thing that's on your notes, I think. The goal here with these concentration and time things here is to convert the rate law into an equation to figure out how the concentration of a reactant is going to change over time. Okay? And so when you have a first order reaction, remember, in a first order reaction, the rate doubles as the concentration doubles. Okay? And so and we're not going to worry about how this equation is derived. Usually when you have natural log type stuff being derived, then it means that there was some calculus involved. So we're not going to worry too much about that. But basically what we've got here is we're taking this rate law and we're changing it into this equation right here as a function of time. Okay, and I think this is the way that it looks on your equation sheet. I can't remember. See if I can find one of those really quick and see exactly how they have it. It might be useful to have your equation sheet out as we're going through this. And the only reason I say that is because most of the kinetics problems are actually on the free response section, so you would have your equation sheet available to you as you're going through these questions. Now on the multiple choice, if they ask any kinetic questions on the multiple choice, you're not going to have it available to you. I'm not finding my equation sheet for some reason. It should be in here. I think I might have loaned all my equation sheets out. Okay, does anyone have an equation sheet that maybe I could borrow for a second just to see how they're written? Thank you. Okay, so when you're looking at it's going to be in the thermochemistry kinetics section, and it's really the three equations at the very bottom of that sheet are the ones that you're going to want to look at. And yeah, I was right here. This is the equation. The first order equation that's written on your equation sheet looks like that. And it's the third from the bottom, okay? And so that's what a first order equation looks like. Thank you. And so that equation, you don't need to memorize that. See, I say that. I guess if they throw a question on first order reactions at you on the multiple choice, then it might be good to know. It's not that difficult to remember this. I mean, basically you got the natural log of your concentration at your final time minus the natural log of your concentration at the beginning is equal to negative kT. And T stands for time in this equation. K is just your rate constant. Okay. So that's your equation there for first order reactions. Okay. So let's see how we use this equation. It's kind of just a plug it in and figure it out type of thing. First order rate constant for the decomposition of certain insecticide in water at 12 degrees Celsius is 1.45 years to the negative 1. Okay, so there's our rate constant, or our K here. Quantity of this insecticide is washed into a lake on June 1st, leading to a concentration of 5.0 times 10 to the negative 7th grams per centimeter cubed. It's kind of a weird way to express concentration, but it works. Okay. And actually, when you take the natural log of something, it ends up being a unitless number anyway, so we don't have to worry too much about our units. But as long as our concentrations are in the same units, then we're gonna call that good. And then we assume that the average temperature of the lake is 12 degrees Celsius. Not that the only reason that matters is because they're basically telling us here that the K that they gave us is good. Okay, we can use it in this particular situation. So, A is asking, what is the concentration of the insecticide on June 1st of the following year? Okay. So, we've got our equation here. So the natural... I just don't have room here. I have room on the next... Ah, here we go. Thought ahead. Minus the natural log of A times 0 is equal to negative KT. Okay? So there's your equation that we're going to use. Okay? And you just have to know what all these things mean. A is basically just your concentration at the end. A0 is your concentration that we're starting with. This is our K, and this is our time. Okay? And the only thing you have to make sure of here is that your time units and your K units match up with one another. Okay, so you got to kind of watch out for that. What is this right here, this concentration? Based on the information they give us. Okay, trying to trick you a little bit. That's what we're trying to solve for. Okay, so this is the one that we're going to keep as a variable. Okay. Minus the natural log of the concentration at time 0, which that is 5.0 times 10 to the negative 7th. Okay, so natural log of 5.0 times 10 to the negative 7th. We're going to have some fun with natural logs today. And that equals negative KT, okay, and our K here is 1.5 years to the negative 1. I think I said 1.45 years to the negative 1. And then what's our T? What's our time here? Okay, now again, it's important that our time units are the same as our K. Since this is in years, then we need our time to be in years. And it's exactly 1 year is the time period they're asking us for here. Okay? So we plug all that in, we end up with the natural log of A at time T, minus, and you can actually, you guys know how to use the log buttons on your calculator, right? And natural log buttons. I assume that you were in a high enough math for that. So if you take the natural log of 5.0 times 10 to the negative 7th. That's going to give you negative 14.5, I think. So you got to be careful with your signs here. Minus negative 14.5 is equal to, obviously, 1.45. And it looks like our units kind of went away on this side, too. Like I said, I didn't include the units up here because when you take the natural log of something, it sort of becomes a unitless number at that point. Okay? And so this is what we end up with. But now, I'm doing this just step by step to make sure no one gets lost in the algebra here, but I don't think you would anyway. Plus 14.5, we rewrite that, equals 1.45. So then, to solve for this, we're going to subtract 14.5 from both sides. We end up with the natural log of a at time t is equal to negative 13.05. Okay. Here comes the tricky part. Does anyone remember when you're solving an algebraic equation how to get rid of a natural log? Because essentially what we want to solve for is this right here, and we've got this pesky thing right here that's keeping us from doing that. You guys remember what you have to do to get rid of a natural log when you're solving something algebraically? I say remember. Some of you may not. Okay, you're close. Now, if you have just a regular log, like if you have the log of x equals 2 or something like that, then you need to take everything to the power of 10, right? So what you would do is, I don't know, I think in math they call it tenning it. You 10 it. So then it'd be 10 to the log of x equals 10 to the second, right? And then when you take 10 to the log of something, it just becomes x, okay? Now with natural log, you don't use 10 because the base for natural log is not 10. What's the base for natural log? It's e, right? So you e it, which sounds weird, but that's what you do here. So e to the natural log of a at time t is equal to e to the negative 13.05. Okay? And so then that's going to cancel out the natural log here, and so you end up with a at time t is equal to, here's my e button, e to the 13.05, and I'm getting 2.15 times 10 to the negative 6. Okay, and again, this is going to be the same concentration as we had before. You kind of get your concentration back at the end here. I know that's weird. Does that seem like a reasonable number? 2.15 times 10 to the negative 6. Let's look back at our initial concentration here. It doesn't seem reasonable, does it? Our concentration increased. Seventh. Let's see if I did my numbers wrong here. Is there anywhere where I messed up on my algebra? Ah, there we go. Okay, thank you. Something was off here. Okay, so this should have been a negative number here, negative 1.45. Negative 1.45, so then minus 14.5, so that should have been negative 15.95 here instead. Okay, so then when we take e to the negative 15.95, okay, there we go, 1.18 times 10 to the negative 7th, that seems better. Okay, so not a huge decrease in concentration, but it did decrease, which is what we would expect over time. Okay. All right. So that's how you plug into that equation. I mean, essentially, it's just knowing how to solve it algebraically, and it's just kind of a plug and chug at that point. I strongly doubt that they would give you a question like that on the multiple choice section. I think that kind of question might be on a free response question. But then you have the equation in front of you that you can use, okay? So that's that. Now, the other thing that they really emphasize on the AP exam is how the graphs of these things look. Okay, so if you plot the natural log of AT versus time, it's going to be a straight line, and the slope is going to be negative k, and the intercept is going to be natural log of A0. Okay, there it is. Now notice something about this equation. Well, actually, let's see. I may have to rewrite it a little bit. Oh, you have it written on your sheet. You guys see right below where it says this. You've got this right here. Okay. So we rewrote the equation a little bit. The only thing that we did here is we put the natural log of A0 on the other side of the equation. The reason for that is because now it looks like something that you're fairly familiar with. Right? Y equals mx plus b. Okay. So what that tells you is your m, your slope, is the negative k. Okay. And you're graphing natural log of a at time t versus versus your t, versus your time. Okay. And then this is your y-intercept, which is essentially what it just said on the other page. Okay. So I don't know who thought of rearranging the equation that way so that you could graph it like that, but pretty cool idea, because then what you end up with, see, notice over here, if you just take the pressure of something, which can be substituted for the concentration when we're talking about gases, but if you just graph the pressure of it, it's not a straight line. But if you take the natural log of the pressure over time, then you're going to get this straight line graph. Okay, it straightens it out. So if you look at a graph on the AP exam and it's the natural log of the concentration versus time, and it's a straight line graph, that tells you right away that's a first order reaction. Okay, and they will do that sometimes. They'll give you 3 graphs and they'll say, what's the order of this reaction? And based on the graph, you need to know whether it's first order, second order, zero order, usually the ones they'll ask you about. Okay. All right. Second order reactions. This is your equation for the second order reactions. Now, on your equation sheet, I'm pretty sure that it is written, I think that this one is written basically the same way as the other one was. It's 1 over a at time t minus 1 over a at time 0 equals kt. Is that the way it's written? Okay. So that's the way it's written on your sheet, but again, it's written like this because this looks like y equals mx plus b. Okay? So when you graph, if you make this your y-axis, and you make the t your x-axis, okay, then that's going to give you a straight line with slope k. Now, which direction is this graph going to be pointing? On the last graph, we had a negative k, right? So on this one, it should be a positive slope, okay? So your graph is going to look like this. Okay, another hint that you're talking about a second order graph is that the line is going to go up instead of down. Okay. Now again, if you just graph the natural log of this, right? If you think, hey, maybe this is a first order reaction, and you graph the natural log of the concentration over time, not going to give you a straight line. Okay. But if you take 1 over the concentration, you take the inverse, which, by the way, that's why it's a straight line going up, is because we're doing the inverse of the concentration, right? On a second order reaction, the concentration is still going down over time. But if you take the inverse of that, then it's going to make the graph go up. Slope of the graph go up. Okay? So that's a second order reaction. Please tell me I included for zero order. I think maybe I didn't. Okay, it's in the sample problem, but we're going to have to talk about that. And we'll talk about it in class, too, because there's some practice problems that talk about the way the graph for a zero order reaction looks. So we'll talk about that in class. All right. So here's a sample problem. Following data were obtained for the gas phase decomposition of nitrogen dioxide. Excuse me. So here's our data, right? Here's our concentration, here's our time, okay? Is the reaction first or second order in NO2? Well, how would we figure that out? Okay, well, I mean, you're right. We have to do an experiment, which they have done, right? So here's the data for the experiment. But how would we use the data from the experiment to figure out what order this reaction is? Now notice, this is different from yesterday's video. Okay, they're not telling us what happens to the rate as we change the concentration. They're just telling us how the concentration changes over time. Okay, so we've got to use what we've been talking about today. It's a little bit easier when you have the concentration and the rate of the reaction. When you can compare those to one another, it's a little bit easier to figure out the order of the reaction. Okay, the only way to really do this well is to graph it. And now I'm debating whether I should make us graph that or not. I think maybe what I'll do is we'll come back to this if we have time at the end. But let's talk about the process here, okay? What would we need to do in order to figure out whether this is a first order or second order reaction? Because that's what they're asking us for. They're saying it's either first order or second order. How would we need to graph it? We would essentially need two graphs, right? Okay. Okay, so we're gonna have to figure out. We could plug into the equations, or maybe the easiest way to do this, given the data that we have, time is going to go on the x-axis for first and second order graphs, right? What's going to go on the y-axis for a first order? Going to be the natural log of, now in this case it's going to be the concentration. Okay, so the natural log of the NO2. Alright, so we would take the natural log of each of these numbers, figure out what the scale on our graph needs to be, and if we end up with a straight line when we graph it, then this is a first order reaction. Yes, sir. Oh, okay. Okay, and then what do we need to graph for a second order reaction? The inverse, right? So it'd be 1 over the NO2 concentration, okay? So you would take 1 divided by each of these numbers, right? Figure out what they are. And then if that gave you a straight line graph, then we've got a second order reaction. Only one of these is going to work, okay? One of them is going to be a curved line and the other one's going to be a straight line. And that'll tell you whether it's first or second order. Does that make sense? Again, they're not going to give you a question like that on the AP exam. What they're going to do is they're going to give you the graphs already made. And you're going to have to figure it out based on the graph. Is this a first or second order reaction? Okay. And like I said, we'll come back to that if we have time. I doubt that we will. And I don't remember off the top of my head whether this is first or second order. So I'm going to have to leave you in suspense on that one. Okay. Half-life. We've talked about this a little bit. Right? You guys remember half-life? When did we talk about half-life? Yeah, nuclear decay, right? I told you this when we did the nuclear unit. It probably flew right by you because we hadn't really talked about it yet. But I told you that all nuclear decay is a first-order process. Okay? Now that should make a little more sense. Okay? What that means is all nuclear decay basically follows... get to it here. Get to the equation. Here we go. It follows this equation right here. Okay? All nuclear decay works this way. Okay. Now I think, did we talk about a when we were talking about nuclear decay, did I teach you the decay equation? Natural log, I think it's 0.693 over T or something like that. You don't remember? Okay. It's been a long time. So, and I'm not even sure, I don't think I even showed you how that was derived. I think I just told you to take my word for it. The thing with the nuclear reactions is those are usually pretty easy. You just, figure out how many half-lives did you have, and they'll give you a time, and then you can usually figure it out. Okay. But half-life is how much time it takes for the concentration of a reactant to drop to half its original value. Okay. If you have 100 grams of uranium, the half-life of uranium, that uranium sample, is how long it would take for it to become 50 grams instead of 100 grams. Okay, and then the other 50 grams decayed into something else. For a first-order process, the half-life is the time it takes for A at time 0 to reach 1/2 A0. Okay. Now, you do not get this equation on your equation sheet, but should you ever need it, should you ever need the half-life equation for a first-order reaction, here's how you get it. It's not hard. If you think about this, you've got natural log of A at time t minus the natural log of A at time 0 is equal to negative kt, right? Well, I'm going to rewrite this natural log of AT, because what is that concentration now, if we're talking about half-life? It's half of this, right? Half of the initial concentration. So I can rewrite this as maybe I should write it this way. Natural log of 1/2 A0, right? Okay. Or actually, tell you what, I think it'll be less confusing as I'm deriving this if I do it this way. This will probably be easier for you to remember. Let's do this. You guys remember if you subtract logarithms from one another, like for example, we've got log of 3 minus log of 2. What's a way to rearrange that, rewrite it? Okay, yeah, log of 3 over 2, right? It's the same thing as this, okay? We can do the same thing with natural logs, okay? So if you've got this and you've got this, so you can actually rewrite this. Gosh, I just not leave myself a lot of room here. Natural log, it's going to be natural log of A at time t divided by the natural log of A at time 0, okay? And that's equal to negative kt. But we just said that this AT here is actually the natural log of 1/2 of A0, right? So if I take this divided by this, I should end up with what? If this is going to be half of that. Yeah. It should be 1/2, right? Not really a trick question. So we end up with 0.5 is equal to negative kt, right? Oh, wait a second. Let me think about that. I don't think that's quite right. Let's just pick a couple numbers. This is this is going to be the easiest way for you to do this. I'm trying to think of a way that you can derive this simply. But let's just pick some numbers, okay? It doesn't matter what numbers you pick, but they need to be exactly half of one another. So let's say that we pick natural log of, what's that? Just 7? Hey, let's natural log of 1. How about? Okay. Well, wait a second. I don't want to get myself in trouble here. Natural log of 1 is 0. Let's not do that. Okay. Natural log of 4. Nope. Did it backwards. I don't like 7. Sorry. Natural log of 2 over natural log of 4. Okay. There we go. So then if you do that, you can actually solve this part of the equation, okay? If you take the natural log of 2 and you divide that by the natural log of 4, what am I doing wrong here? Yeah, I know. I need to get the number 0.693. Oh, there we go. Okay, Yeah, so natural log of, we need to take the natural log of 0.5. That's what it is. Okay. Thank you. All right. I apologize for the confusion here. So what we need to do here is natural log of 2 over 4, like this, okay? So that's going to give us the natural log of 0.5, okay? And then when we do that, you end up with the number negative 0.693 something, okay? And that's equal to negative KT. So then if we get rid of the negatives here, you end up with 0.693 is equal to KT. I may do this derivation again in class because this is going to be confusing on the video. So 0.693 is equal to KT. That's kind of your half-life equation, and I think the way that it's usually written is 0.693 over K is equal to T, because, you know, you're trying to find the half-life, the time that it takes for it to decay that amount. So it would be 0.693 over K. All right. Okay, sorry about the confusion there. I should have put this in parentheses up here from the very beginning. All right. So for a first-order process, notice the half-life only depends on K. Okay, because notice when we finally rewrite this equation right here, the only thing that makes a difference is this K right here. Right? We got rid of all of our concentrations here when we are doing this reaction. So that's why for the half-life of uranium, if it's 1 billion years, then it takes 1 billion years for that uranium to decay from 100 grams to 50 grams. It takes another billion years for it to decay from 50 grams down to 25 grams, okay? Because it's a first-order process, the decay rate it's not affected by the concentration, okay? Now that's not the case for a second-order reaction, okay? But first order is usually when we're talking about half-life. Okay, so again, notice this is just an example here of CH3NC, and the pressure as that changes over time. This must be a first-order process here, okay? Because, whoops. What are you doing? Okay, so it goes down from 150 to 75. That's your half-life, and that takes about, I don't know, somewhere around 14,000, 15,000 years, a little bit, probably 14,000 years, okay? And then notice your next half-life, to get from 75 down to 37.5, is at about 28,000 years, okay? So it's 14,000 years consistently each time you have a half-life. To get the second-order half-life equation, again, I don't know, let's see, how much time do we have? This is probably useful to talk about. I don't know that this one is ever going to be as necessary, but just in case, okay? Now again, you don't ever really have to derive this, as long as you remember that half-life is, your AT is going to be half of your A0, okay? And as long as you can plug that in, then you should be fine. But the half-life, or sorry, the second-order equation here is 1 over A0. Is that right? No, it's 1 over AT, isn't it? I forgot already. Is this right? Equals KT. Okay. So then on this one, we just have to plug in, again, you can plug in any number you want, and it'll be fine. We can use 2 and 4 again. So let's see, 1 over our AT would be the 2, minus 1 over 4 is equal to KT. Okay. And so for this one, we're going to end up with 1/4. Make sure I'm thinking about this right. Yeah, we better keep it more generic, because on this one you actually, the numbers, if you change the numbers, then we're going to actually change the way that it works. So 1 over, I was trying to avoid something like this, but I think this is the way this one has to be done. No. I apologize. I should have been more prepared for these derivations this morning. Well, that's why that keeps happening, because I'm hitting this thing. I didn't know this could adjust the volume. I think our 2 and our 4 would work here, wouldn't it? You know what? I'm sorry. Just for the sake of time, I'm going to have to get back to you on that one in class. Okay. This one does depend on the initial concentration of the reactant, so we'll like I said, I'll derive that one for you in class. Which will be, will that be today? Or is it tomorrow? No, it's Monday that we're covering 14.4, so I'll derive it on Monday. Okay. Okay. So sample problem here. We've got 3.0 grams of something decomposing for 36 minutes. The mass of A remaining undecomposed is found to be 0.60 grams. What's the half-life of this reaction? Okay. Well, I forgot to tell you an important piece of information here, which is that this is a first-order reaction. Okay. And I'll make sure and tell you that on the test, because you need to know that. Okay, so now we know which equation to use if it's first order. So we've got 3.0 grams decomposing for 36 minutes, and the undecomposed is 0.60 grams. So we want to know what's the half-life of this reaction. Okay, now this is an example of one that might be kind of difficult to solve the way that we solved the half-life problems at the beginning of the year. Because if you notice, this doesn't work out, these numbers don't work out quite so nicely, right? So you got 3.0 divided by 2, 1 half-life, it would be at 1.5. At 2 half-lives, it would be at 0.75, right? And so this is not going to fall into a perfect half-life there. So that's where this equation actually comes in handy. Since this is the first order, we know that we can use this equation here, natural log of A at time t minus the natural log of A at time 0, and it's equal to negative kt, okay? Now, is that equation going to give us the half-life of this reaction? What is that going to tell us? Okay, here, it's actually going to tell us the k, right? Because we need to solve for k here before we can figure out our half-life. Okay, so we have all the other pieces of information we need in this equation. We just need to solve for k, and then we can do the half-life thing. Okay. So our natural log of, what's our concentration at time t? Yeah, again, grams, kind of weird for concentration, but usually we can use any amount and this will work for us, okay? So natural log of 0.60, I need to put that in parentheses, but and then our concentration at the beginning time is 3.0, okay? Gotta make sure that you get those right. And that's equal to negative k times our t here is, okay, and we'll just keep it in minutes. What that's going to do is it's going to make our k here, it's going to give it the units of minutes, or minutes to the negative 1, okay? So just keep an eye on that. Okay, this one's nice and easy to solve because we don't have to e anything because we've got, you know, both of our natural log things will just be numbers once we plug this in. So the natural log of 0.6 minus the natural log of 0.3, or sorry, the natural log of 3 gives me negative 1.609, and that's equal to negative k times 36. Divide both sides by negative 36. I'll get rid of the negative. And our k here should equal 0.045, okay. Good job on the sig figs. 0.045 minutes to the negative 1, okay? So now that we have our k, you can do one of two things. You can do the derivation we talked about, or you can just remember this. that the T1 half is 0.693 over K. All right. Now, if you forget this number, just remember in our derivation we had to take the natural log of 1/2, or the natural log of 0.5. Okay. So if you plug the natural log of 0.5 into your calculator, it's going to give you that 0.693 number. Okay. All right. So now that we know our K, we can just plug that in up here. 0.693 divided by 0.045 minutes to the -1, and that's going to give us our half-life in minutes, okay? Which should be about 15.4 minutes. Okay, now it's always a good idea on these to check and make sure that our answers make sense. So this thing goes from 3.0 grams down to 0.6 grams in 36 minutes. Does it seem reasonable that one half-life would be about 15.4 minutes? I mean, it seems like it's in a reasonable range. Okay, so we're probably on the right track there. Okay. Given that the reaction order for the reaction A to B is 0, 1, or 2, use the information in the graphs to answer the following. Okay. Now, in this particular question, you don't have to know what a 0 order graph would look like. Basically, a 0 order graph looks like this. And again, I said we'll talk about that in class, okay? But notice how for a 0 order, it's just concentration versus time, okay? So this would be a 0 order. Natural log of the concentration would be a first order. And then 1 over the concentration would be a second order. Okay. So which one of those graphs gives us a straight line here? Yeah, first order, right? It's the only one that has a straight line slope. So this is a first order equation. Okay. And all you have to do is just look at the graph to figure that out. Whichever one gives you a straight line, that's the order reaction we have. Okay? Now, it may be useful here to just kind of... Is that the last thing on your notes? There's one more. Okay. Let me just take a step back for a second here, because I think we have time. Just to remind you, what does 0 order mean? It means you can change the concentration however you want, and it's not going to speed up or slow down that chemical reaction. Okay? What about first order? Okay, if you double, it does whatever the concentration does, essentially. Okay, if you double the concentration of your reactants, that doubles the rate of the reaction. Okay, now what about second order? What happens if you double the concentration of your reactants in a second order? It quadruples the rate. Okay, so that's how you figure that out, or that's what that means, I guess. Okay. Determine the order of the reaction with respect to A. Oh, wait, we just did that, didn't we? So we said it's a first order based on the graphs. What is the rate law for this reaction? Okay, so here's our equation right here, A to B. Now, we always write our rate law with respect to what? Reactants or products? It's reactants, right? Okay, so we talk about the rate of disappearance of the reactants. So anytime you write a rate law, it's going to look like this. Rate equals K times something, okay? Now, which concentration matters here? Concentration of A, right? And if this is a first order reaction, then our exponent is just a 1, which you don't even have to put the 1, okay? It's just understood. So there's your rate law. Okay? And then what is the rate constant for this reaction, including units? Well, how would we figure that out? Okay, right. The K is our slope, right? Actually, K is the negative of the slope. You want to have a positive K. Alright? So we can just pick some numbers from the graph here, which, can you see that well enough on your thing to fix? Let's see here. -2. Negative 3.4 is on a point. At time 10. You mean negative 2.6? Okay, so negative 2.6 and 10. Okay, so negative 2.6 and 10. Let me think about this. Negative 2.6 is our y, right? So basically we're just finding the slope. We're doing rise over run here, okay? And then what's another point that's close? Looks like maybe maybe negative 3.4, possibly. That's close to 18, I think. Negative 3.4 and 18. Was that the bell? No, that wasn't the bell. Okay. Okay. So then you just plug that in, basically, and you should be able to figure out the slope of your graph. 2.6 plus 2.4. And it looks like it's about 0.1. Now, the way I wrote this, it's negative because this is a negative slope, right? But yeah, you change that to a positive because k is going to be the opposite of your slope. Okay. So our k here is going to be, 0.1. Now, what are the units for this reaction? Okay, it's a first order, so it's just going to be your time, and it's seconds to the negative 1. Okay? Alright, so that's that. Again, we'll cover some of this in class that I didn't get on the video, especially the derivation we'll do. So, alright, see you next time.